Welcome to qnawire.
So we have a rotating planet, and we're given the weight of an astronaut on the pole and the equator. And we're ultimately asked to find what the period of rotation of the planet is. So that sounds to me like we'll be using the fact that there's a centripetal force acting at the equator. And so by looking then at the difference in force the astronaut experiences, we'd be able to figure out what the centripetal force is and then what the velocity that of the astronaut at the equator, and so therefore what the velocity of rotation is of the planet. And so once we have that velocity, then we should be able to figure out what the period is. So we'll start by writing out force equations here. So basically what we're told is at the equator, the force on the astronaut is 850 newtons. And so that must equal just the force of gravity on the astronaut. So mass of the astronaut times, I'll say a sub x, so the acceleration of gravity on planet X. And then subtracted off from that, we have the centripetal acceleration, which is going the opposite way. So we have mass of the astronaut times velocity. So this is rotational velocity, or also the velocity of the astronaut at that point, and then divided by the radius of planet X. So let's try to solve for the velocity, and once we have that, we'd be able to figure out what the period of rotation is. So first we'll move this term to the other side, so we can say then that negative ma v squared over rx, kind of flipping this all around. So that will equal then a 50 newtons minus mass of the astronaut times acceleration on planet X, and then we'll get rid of this negative sign. So mass of the astronaut, v squared over rx equals ma ax minus 850. And then we'll say v squared equals rx over ma, and that whole thing is multiplied by ma ax minus 850. And then finally we can get v by itself. So square root, and we can simplify things here a little bit, and we should end up with square root of rx minus ax minus 850 over ma, mass of the astronaut. So once we have this velocity, we can just say that the period should be 2 pi rx divided by the velocity. So let's start trying to deal with these terms in here. So rx, we need to know the radius of the planet. Well, they don't directly give us that, but they tell us that on this planet, if we go from the equator, or from a pole over to the equator, so this distance, they tell us that that is 18,850 kilometers. So this looks like it's just a fourth of a circumference around the planet. So 1/4 of the circumference of 2 pi rx equals, that's 18,850. And so then we can solve for rx as 1.2 times 10 to the 7th meters. So there's our Rx in the equation. So now we just need A sub x and ma, mass of the astronaut. So let's get A sub x next. The order here doesn't really matter. So we know that they also tell us that on Earth, the astronaut weighs 945 newtons. So mag equals 945. And so using g is 9.8, we can get that the mass of the astronaut is 96.2 kilograms. And so then given that at the pole on planet X, where there'd be no centripetal force acting, the astronaut weighs 915 newtons. That should be mass of the astronaut times ax. And so then kind of plugging in this 96.2 for MA, we can then find that AX is equal to 9.51 meters per second squared. So we found RX so far. We've got an AX. And we also got mass of the astronaut here. So that's everything we need then. So we can plug all those in, and we get then that the velocity at the equator of the planet is 2844 meters per second. Okay, so we'll go on to a new page here. And so then we know the period of motion of rotation should just be 2 pi rx over v. And so then using those values we just found, we get that this period is 2.65 times 10 to the fourth seconds. And that would come out to be 7.36 hours. So then part B asks us about a satellite orbiting. And so they give us the height. So really all we have to do is, we know, so the satellite's in circular orbit, as we've seen many times, that velocity of its orbit will just be 2g m over r. And we know also that the period, as we just used, is 2 pi r over v. And so we've combined before these two equations to say that the period is the square root of 4 pi squared r cubed over gm. So this is probably a good equation to kind of have written down somewhere too. So all we did was just plug in v, this quantity for v down here, and then simplify a little bit, but it can save you a little time just to have this result handy. So with this, all we want to do is plug in rx for r, and then mx for m, and that'll give us the period of this. So I don't think we ever actually found mx, and so we can do that by saying that we know the acceleration on planet X should just be g times the mass of planet X over rx squared. So that's true on any planet, including this one. And so we know rx, we know g, so we solve for mx as just ax rx squared over g, and that should come to be 2.05 times 10 to the 25th kilograms. And so now finally, using our value of r from the previous equation, the previous page, and then the value of m we just found, we get then that this period is going to be 8.90 times 10 to the third seconds. And so that comes to be about 2.47 hours.